Hey everyone, Mr. Smith here, shooting a video for my grade 11 split class, the 3M class and the 3U class in the same class, but we are doing the same topic today, so I'm just shooting a video for everybody. I'm away to swim meet today, and then who knows, maybe the YouTube population will enjoy this as well. Yesterday we saw during the warm up that our calculators, when we did at a power of zero or an exponent of zero or a negative exponent, our calculators actually gave us an answer, which seems weird because what does it mean to multiply by a number by itself 0 times or like -2 or -3 times? Today we're going to look at that. So for the 3U students, you did look at zero negative exponents in grade 10, or at least it's in that curriculum. For the grade 10 applied students, this will be new for you. So kind of a review lesson for some, new for others. So we're going to try to find an appropriate balance and pace. And then when it comes to demonstrating our learning, it's possibly the 3U students might be expected to do a little bit more with these zero and negative exponents in some practice or some assignments. But at least for the lesson, we can all do this together. So I've got a little investigation for us to do, a little table to complete. At least when we look at this first row, you might think, why are we doing this? Because we're simplifying this expression 2 to the power of 3 divided by 2 to the power of 1. And in the second column, we're going to expand out. 2 cubed means 2 times 2 times 2. 2 to the power of 1 is 2. And when we expand that out, we get 8 divided by 2, we get 4. Hopefully you're convinced that 2 cubed over 2 1 is 4. Now, we just learned some exponent laws, actually, or reviewed them. When we're dividing two powers, we can actually subtract the exponents. 3 minus 1 is equal to 2. So 2 to the power of 3 divided by 2 to the power of 1 is the same as 2 to the power of 2. So what we've just shown, if you compare these two rows, we've shown that expression is equal to 2 squared, but it's also equal to 4. So we can conclude that 2 squared is equal to 4. I know it's not earth-shattering for anybody. We already knew 2 squared was 4. But let's continue this with while continually increasing the power of what's on the bottom. So what if we add an extra factor of 2 on the bottom, 2 squared? Well, 2 times 2 times 2 is still 8. 2 times 2 on the bottom is 4, and 8 divided by 4 is 2. If you subtract the exponents, you get 2 to the power of 1. And our conclusion is that 2 to the power of 1 equals 2. We already knew that. But what happens when you try the next one using the same process? So can you pause the video if you're watching at home and try completing the next row in a similar manner? And then unpause when you're ready. I'm going to just go ahead. So 2 cubed divided by 2 cubed. It's like 2 times 2 times 2 divided by 2 times 2 times 2. And that gives us 8 over 8, which is equal to 1. So nothing shocking there. But what happens when you use your exponent laws and you subtract those exponents? You get 2 to the power of 0. And the conclusion that we can make is that 2 to the power of 0 is equal to 1. We've just actually verified that 2 to the power of 0 is equal to 1. You can try that on your calculator right now if you'd like. Give it a go. 2 to the power of 0 is 1. And I would argue if I change this base to be 4 to the power of 3 and 4 to the power of 3 and do the same thing, I would get 4 to the power of 0 is 1. If I change the bases to 5, I would get 5 to the power of 0 is equal to 1. The fascinating thing is any base that's not 0, things get a bit weird that you got to wait till multivariable calculus to look at 0 to the power of 0. But anything to the power of 0 is equal to 1. So let's get that down. We've just shown that the following is true. A to the power of 0 is equal to 1 as long, we'll just say if a is not equal to 0. We won't touch 0 to the power of 0. Why does it work? So if you look at what we did there, raising something to the power of 0, it's like dividing a power by itself. That's where the exponent of 0 comes from. So, and we know that when you divide anything by itself, you wind up getting 1. So why does it work? I don't want the compass, I want my text box. Why does it work? When you divide anything by itself, you get 1. Now, I have the teeniest, tiniest bit of space here, so maybe I can just convince you one more way. Let's do 5 to the power of 3 divided by 5 to the power of 3. Of course we know this is equal to 1. It would be 125 divided by 125. It's equal to 1. Anything divided by itself is 1. But also, 5 to the power of 3 divided by 5 to the power of 3, using our exponent rules, is 5 to the power of 3 minus 3. It's 5 to the power of 0. We've just shown 5 to the power of 0 equals 1. So hopefully you're convinced, and that's a really cool thing coming into today. You can have an exponent that's 0. The result is 1 all the time. But we're not done. Let's go even further. What happens if we keep going and we add another power of 2 onto the bottom? So 2 times 2 times 2. We have 4 factors of 2 on the bottom. Now, I'm going to leave this as a fraction here. I get 8 on top still. I get 16 on the bottom. 8 over 16 is correct. 0.5 is correct too. But I think it's worthwhile to leave that as 1/2 for now. 2 cubed over 2 to the power of 4, when it comes down to it, is equal to 1/2. And if you use your exponent laws, 2 to the power of 3 minus 4, 3 minus 4, we're now into the negatives. We get 2 to the power of negative 1. Our exponent laws give us 2 to the power of negative 1. Crunching the numbers gives us 1/2. We've just shown that 2 to the power of negative 1 is equal to 1/2. We can do powers that are negative. The rule, though, isn't quite clear just yet. That was only our first example of a negative exponent. Let's see if we can find a pattern by increasing the power on the bottom a couple more times. So with 5 2's on the bottom, we get 8 on top, 32 on the bottom, and that's 1 over 4. If you do 3 minus 5, you get negative 2. 2 to the power of negative 2 is equal to 1 over 4. Very cool. Now, just with those 5, it is possible you see a pattern here. Look at this. 2 squared is 4. 2 to the power of negative 2 is 1 over 4. 2 to the power of 1 is 2. 2 to the power of negative 1 is 1 over 2. When we do 2 to the power of 3 minus 6 here, we get 2 to the power of negative 3. Do you think you can predict what this will equal to? You can pause the video and think about that if you'd like, or we can find out by doing one more power of 2 on the bottom. That gives us 8 over 64, which is 1 over 8. We have just shown that 2 to the power of negative 3 is 1 over 8. There is a pattern here, and before I actually fill in this rule, I'd like us to just maybe fast forward in this note just a little bit. So if we go to this visual summary for powers of 2, on our lesson sheet, we have the following. We've already done 2 to the power of 0, we showed it's 1. 2 to the power of 1 is 2, we knew that. 2 squared is 4, 2 cubed is 8. 2 to the power of negative 1 was 1 over 2. 2 to the power of negative 2 was 1 over 4. And 2 to the power of negative 3, we just showed, was 1 over 8. There's some symmetry here. There's a pattern. Can you see it? And can you predict what the value of 2 to the power of negative 4 would be? Again, you can pause the video and unpause when you're ready. But if 2 to the power of 4 is 16, That means 2 to the power of negative 4 will be 1 over 16. Very fascinating. And I think we can see if you guys have this idea by looking at powers of 3. So powers of 3, we know, hopefully, you're convinced 3 to the power of 0 is 1. 3 to the power of 1 to the power of 2, those are all things we can compute on a calculator. 3 cubed is 27. 3 to the power of 4 is 81. But can you apply the same rule from above with the powers of 2 to the powers of 3? Pause the video, unpause when you're ready. So if 2 to the power of 1 was 2, 2 to the power of negative 1 is 1 over 2. 3 to the power of 1 is 3. 3 to the power of negative 1 is 1 over 3. If you got that, good for you. 3 squared is 9. 3 to the power of negative 2 will be 1 over 9. That's the pattern. What's 3 to the power of negative 3? Well, it's 1 over whatever 3 to the power of 3 is, 1 over 27. And then finally, 3 to the power of negative 4 is 1 over 81. So we've investigated this rule. We've looked at some of the visual patterns here. Let's summarize this rule. The rule for negative exponents is this. If you have a base to a negative exponent, this is equal to the reciprocal of the positive exponent, the power with the positive exponent. I'm going to add this term in here. So by doing 1 over, this is a fancy, the reciprocal is a fancy word for flipping or doing 1 over that. So reciprocal or flip. Some of you guys might just prefer flip. And why does it work? So loosely speaking here, this is my own words, not something from a textbook or something formal. But loosely speaking, negative exponents are like dividing a small power, a smaller number, by a larger number, giving a fraction. So if you're a pure math student at a university somewhere and you're like, Mr. Smith, that's not exactly correct, the goal here is to give something that the newer students, grade 10 applied students, can kind of visualize. When you have a negative exponent, loosely speaking, it's like you're going to have a smaller power on top and a bigger power on the bottom, and that's going to give you a fraction, like it did in our table here, right? Smaller power, 2 to the power 3 on top, larger power, 2 to the power 6 on the bottom. It gives you a fraction, 1 over 8. So if that helps you, that's good. Just to give you another example of kind of that result, let's do something on the fly here. Let's do, I don't know, what would happen if we did 5 to the power of 4 divided by 5 to the power of 6? Well, using our exponent rules, that would give us 5 to the power of 4 minus 6, 5 to the power of negative 2. It's a little weird when you think about it as, oh, this is just a larger number divided by a smaller number. Five to the power of 5, I might write it out this way actually. And then 6 powers of 5. I was gonna try to do 5 to the power of 6 in my head and thought, no way. But if you just think about dividing out all the pairs of 5s, you're left with 2 on the bottom. So all those things dividing out, giving you 1, and then 5 times 5 is 25. So you get a big power over a small power over a big power, gives you this fraction, 1 over 25, this negative exponent. And this makes sense according to our rule. Since 5 squared is 25, 5 to the power of negative 2 is 1 over 25. So we've developed these rules or reviewed them. Let's put them into practice a bit. For each of these sections, it'd be great if you just did these on your own and unpause the video when you're ready. So hopefully you've done that. I'm just going to slam these out. Now, really, we should just be able to whip off A, B, C, and D here, they're all just 1. Remember, anything to the power of 0 is 1, as long as it's not 0 to the power of 0. So let's try the next 3, working with negative exponents. Review for some. So for the grade 10 applied students, hopefully things connected. Now I think I stole a bit of my thunder for this one. So 5 to the power of negative 2, what is that equal to? Well, we know that it's going to be the flip, 1 over, of whatever 5 to the power of positive 2 is equal to. So we rewrite in terms of positive exponents, and now 5 squared is 25, 1 over 25. Now I should note, if you punch this into your calculator, some of your calculators will give you 1 over 25. Some of your calculators would give you 0.04. For me, to get evidence of learning, I want to see you applying this rule for negative exponents. So I want this intermediate step. Anybody can just punch this into a calculator. That's not the goal here. I want to see that rule being applied. Let's do it for B. What is 6 to the power of negative 3? Well, whatever it is, it's going to be the flip, the reciprocal, 1 divided by whatever 6 to the power of positive 3 is. 6 to the power of positive 3, we can do it in a calculator. I believe that's 216. So 1 over 216. C is an important one because in part C, the base is negative and the exponent is negative. So you need to be careful. When you use your rule, the base doesn't change. What is negative 2 to the power of negative 4? Well, it is 1 over whatever negative 2 to the power of positive 4 is equal to. Notice I did not make the base positive. Now I can do negative 2 to the power of 4. Use brackets on your calculator. It should give you positive 16. 1 over 16. Okay. We can actually do negative exponents for fractions where the base is a fraction as well. I said yikes jokingly, but we can handle it. The rule is very similar. So let's say you have a fraction. I'll just call it a over b. And you raise that to an exponent, a negative exponent. We'll say negative c. The rule is very similar to what we've been doing. You flip. So you take the flip, which would be b over a. And then you change the exponent to a positive. So the rule looks a bit different, but it's the same. We flip and we change the exponent to a positive. So let's give this a try. So 1/5 to the power of negative 3. For some of you guys, fractions you already find hard enough without adding in negative exponents. But using this rule, we're going to see this works out pretty nice. What's the flip of 1 over 5? What's 5 over 1? And we change the exponent to positive 3. Now, you could have just flipped 1 over 5 to be 5 right away, but this is just 5 cubed. 5 cubed we can do on a calculator. It works out to exactly 125. And you can try using brackets, using your fraction button. 1/5 to the power of negative 3, it does give you 125. But I would like you guys to see, I would like to see this being applied. For B, I think I'll just work downwards from here actually. Don't want to blend into this. So 3 over 4 to the power of negative 2. How do we evaluate this? You flip 4 over 3, and then you change the exponent to a positive 2. At this point, we can use our rule from yesterday. Just everything in the brackets gets the exponent of 2. 4 squared, 3 squared, 4 squared is 16, and 3 squared is 9. Quite possibly, you went right to 16 over 9, and that'd be totally fine. Okay. So what is left for us to do today is for the students who took grade 10 applied, we really want to do a lot of practice and really get used to this idea of exponents being 0 and negative. Just practice, practice, practice. For the grade 10 people that took grade 10 academic, it's possible that this didn't stick last year and you should practice, practice, practice too. If it's coming back, that's good. Still practice, make sure things are rock solid, but you could also help those around you as well, right? Okay. The last thing I want to do in this lesson is just look at an application of negative exponents. And that comes from something we call scientific notation. So not everybody is taking the university level science courses, but I believe in even the other like college level science courses, or just you know uh, watching YouTube or the scientific notation is going to pop up, and we use scientific notation to take numbers that are really, 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 really big or really, 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 really small, and just write them kind of in a more concise way. So, for an example, the diameter of a single proton is about 0.00000000000000001, which is kind of a mouthful to say. It also is a kind of a pain in the butt to write down. Instead, what we would say, we can write that more simply as 10 to the power of minus 15 meters. Another example here is the diameter of the nucleus of an atom, which would be 10 to the minus 10 meters. Now, am I stealing my thunder with this down here? I am not. 10 to the minus 10, that's a much nicer way to write 0.00000000001 meters. It's just a lot more practical. So this idea of taking these small decimal values and writing them as a power of 10. And now we understand a bit better. Like 10 to the minus 10, I'll squeeze this here. Well, we know now that's like 1 divided by 10 to the power of positive 10. It's a very, very, very tiny decimal. 10 to the power of 10 is like 10 billion. This is 1/10,000,000th. A nicer way to write that, instead of using all the decimals and zeros, is to just write this as 10 to the minus 10 meters. Now, how do we go back and forth between these really small decimals and these powers of 10? So I'll tell you a rule. For this first one, if you count out all the zeros, including the zero out front, there are 15 zeros. You can take my word for it or count them up here. That's why it's 10 to the minus 15. That rule works all the time. So, however, for numbers that aren't factors of 10, like 0.000000034, what you can do is count the zeros, and then that gives you your power of 10. So here we have 1, 2, 3, 4, 5, 6, 7, 8 zeros. We can write this number as 3.4 to the times 10 to the power of negative 8. Still a lot cleaner and a more compact notation than writing out the huge decimal. But the rule is simple. So if you have the digits like 3, 4, you write 3.4. Always treat the first number as like a whole number, and then a decimal, and any number that comes after it, and then just count the zeros. That gives you your power of 10. Just make it negative. So here's a few examples. Thickness of a human hair is 0.00005 meters. So how do we write that in scientific notation? We take the 5. It's just 5, so you write it as 5.0. Count the zeros, 1, 2, 3, 4, 5, 10 to the power of negative 5. The mass of a grain of sand, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros, hence the 10 to the minus 11. And the non-zero digits is just 3. So 3 times 10 to the minus 11. Can you try this one? The mass of a proton is so small, and this would be kilograms. I should add on here. You can pause the video, unpause when you're ready. Here we go. 1, 2, 3, 4, 7, 10, 13, 16, 19, 22, 25, 27 zeros. 1.7 times 10 to the minus 27 kilograms. 27, because 27 zeros. Why 1.7? You take the non-zero digits and you just take the first digit as your whole, so 1.7. You can work backwards and try this one for yourself. So 1.5 times 10 to the minus 8 meters. That's the wavelength of some UV light. Very, very tiny. How can we write this in terms of a decimal? Well, the 10 to the minus 8 means we have 8 zeros, including the 0 front. So 1, 2, 3, 4, 5, 6, 7, 8, and then 1.5. We just tack on 1.5. One more and we wrap things up. The time it takes light to travel from the blackboard to your eyes in like a typical classroom. 1, 2, 3, 4, 5, 6, 7, 8 zeros. 10 to the minus 8. It's in seconds. And then the non-zero digits are 3 and 3, so 3.3. Now, if you're in my class watching this at home, I'm not going to be testing you guys on scientific notation. But it's useful, it's applicable. If you're in the sciences, things are in scientific notation. It's how we express large numbers and small numbers, like in this case. But it's just a neat application that is used every day in the sciences of negative exponents. All right. Hope you guys enjoyed the video. As usual, take care, and we'll see you soon.